Roots. Okay, I'm working with functional programming for the last 3 years on one of the Dutch projects. I will talk about that later. So first of all, I want to make a short introduction about teaching and listening. Можете выключить музыку? Кто там на пульте? Кто на пульте? Please turn off the music. It seems they want to dance, yeah? Then they don't want. Okay. Thank you very much. Thank you. Okay. So, as I have said, I want to make a short introduction about teaching and listening. So everyone sitting here will understand me better. So, we will talk about math today, and I guess that many of you associate that word with the word boring. Maybe, no? No? But some people imagine the room full of sleeping students at the calculus lecture, right? But I want to stress that this is not a lecture. I'm not going to teach you. I'm not going to give a lecture for you. First of all, I want to say that you mustn't believe me. I'm not authority. I could be wrong. You must listen by yourself, ask me question, and let's think together, guys. Let's inquire and discover the problems together. I want to have a dialogue with you, not a lecture. I'm not professor. You're not students. We're just people who are talking with each other. If you come back to the problem with professor and students, we could ask the question, why students cannot grasp the essence of the calculus definitions at the very first second they hear it? Why? I guess that problem appears because of how the understanding works, actually. Because students has a lower level, and professor has maybe some higher level of understanding. To understand, we need to meet at the same time, same place, and at the same level. We need to use the same vocabulary. The words must mean the same. And it's very hard to transfer your knowledge with unknown words, right? So I will try to talk as simply as I can. And I want to ask you not to fear the unknown words. Try to look sharply, and you will see that the picture behind is very simple, actually. It's not so difficult as it might be in your fantasies. Okay, so that's the finish of introduction. And I will come to the first really serious question. What is the programming? We could say that what are we doing as programmers, as software engineers? We are tackling some problems. We are trying to find the solutions. From the OOP point of view, sorry for that, I guess. We are on a functional programming configuration. But from the OOP point of view, we're trying to find the main entities. For example, here is a problem with graphical user interfaces. There are some classes, buttons, panels, and so on. Some inheritance, among them. So there is also sequence diagram which shows us how those entities interact with each other. As you can see, we have the arrows, and arrows are like actions, and objects is like classes, right? And objects are connected with arrows. Okay, so what we are doing here, we'll talk later, but let's at first look at the functional programming point of view. From the functional programming point of view, we're working more like with pipelines of actions. So we could have some MD action, then to HTML action, and then post-process action, which is composed of visit, post, and other sections. It's kind of big pipelines. And now those arrows are not actions. Now objects are actions, and arrows are types. Functional programming types. Some text, some HTML, some decorated HTML, and so on and so on. Okay? So what is similar between those point of views? I guess the similar is that we decomposing problems to the smaller ones, decomposing it to the entities and the relationship between those entities. And that the short answer is the similarity between those is composition. So I want to stress out that programming actually is just a composition. We just decompose problem to the smaller one and then recompose it to the bigger one, okay? After solution of some small bunches of tasks. So, is there any science which is focused on composition? Yeah, there is, and it's category theory. Why to study category theory, you may ask? Here you see a graph which indicates the number of times using the phrase category theory in the scientific articles and books. You could see the source there. I guess you may attend that after the talk, not lecture, sorry. Why to study category theory? First of all, it's extremely general. It's really general and wide applicable. It gives a new way, not that theoretic, to look at the foundation of mathematics and programming, and also it connects many different fields and give a way for the specialists from those fields to talk one with each other. So, for example, specialists in biology could talk with quantum mechanical physicists and so on, or maybe some topologists and mathematics, or maybe even programists, okay? I want to show you this quote from one of the articles I read. I crossed the topology and algebra and wrote the program in there. So category theory makes very hard and entangled problems very simple ones. It just abstracts all the mass around the problem and throws it away. So you can see clearly the essence of the problem, and in many times, you could solve very hard problems simply. That's why, I guess, that is the main reason, I guess, why we need to study that. So, why to study category theory for software engineer? First of all, we encounter with much more complex problems nowadays. For example, it's really those are appearing because of multi-core revolution and distributed systems revolution. Also, category theory is a source of extremely useful programming ideas and patterns. Haskell programmers are tapping on this source for years, but we need to make this process more broad and more fast than it is now. Also, it gives you a great theoretic foundation for programming. People who love math, oh, they must know it, actually, if they are programmers. So category theory also is a kind of math that is particularly well suited for the minds of programmers. And I guess the key here is the composition, which I mentioned before. So what is category? I want to show you one and very simple picture with piggies. So that is category. Object there is piggies, and they shooting the fireworks at each other. So it's very simple. There is an arrow from A to B, piggy, and from B to C. And if there is those arrows, there must be some arrow from A to C. Okay, take a photo. Okay, great. If we look at that more abstractly, category is objects, arrows between those objects, and the rule of composition. Rule of composition here is a function that takes two arrows, as you can see, or functions, from A to B and from B to C, and returns the next arrow from A to C, like on the picture with piggies before. Okay. Also, we need to have a associativity of composition. It just means that it doesn't matter what is the order of operation is. It's the same as with addition or multiplication in algebra. So it's just the guarantee that order doesn't matter. That is the other picture, which shows which shows that actually this rule is guarantee that the arrow from A to D composed differently. So two different paths from A to C and from C to D, and from A to B and from B to D are equivalent, or equal, actually. So one more time. Why is associativity is important? Because of the order of operation doesn't matter. And actually with pure functions, that is so. If functions are pure, then order of operation doesn't matter. In C++, if we will use not pure function, oh my god, it won't be held no more. Also, we need to have identity arrows. Identity arrows is an arrow from object to the same object, which does nothing, actually. So, does nothing property is actually those equations. It means that if you take any other arrow from that object to any other object and compose it with identity arrow, we will have the same action. So it's kind of zero. It's kind of zero for composition, if we will make an analogy with addition, for example. If you will look at the diagram, it will look like that. So it doesn't matter how many times we will encircle the A object by the arrow ID A or B object by the arrow ID B. We could do that infinitely many times. We still have, after the composition, the action F by itself. So why do we need identities? As I have said, it's natural element for the composition, and also it gives us a possibility to define the notion of sameness. As mathematicians said, isomorphism. So isomorphism, actually, it's just an arrow that can be undone. It means that it has the inverse to the other side. We will not need that now. So let's talk about the basket of cats. Some examples, okay? As you have seen, piggies, those are more abstracted piggies, and that is a category 3. It consists of 3 objects and just 2 morphisms with their composition. So actually it has 3 morphisms, 3 identities, and 3 objects. There could be even simpler categories, for example, 1 piggy with 1 identity arrow is category 1. And even simpler, category 0 with no objects and no arrows. But that's not interesting, I guess. Let's move to more interesting examples. Integer category. Integer category consists of the singleton. By singleton, I mean the set with 1 element inside it. It's just a dot. And the arrows there will be all possible integers. Composition is an addition of integers. And identity is, for that singleton object, is 0 integer. By analogy, there is string category. Object there is only 1 object, singleton. Arrows, all possible strings. Composition is concatenation. Identity is an empty string. You can see the properties of associativity and identities below. In mathematics, those structures, strings, integers with multiplication and 1 and also addition 0 are called monoids. Monoids are very applicable in programming. And from the set theoretic approach, it's like just a set with binary operation in it, which is associative. And also there exists some natural identity element that for all A and M, we have the identity property. From the category theoretic approach, it's just a singleton, and arrows are that set M, so all the integers or all the strings, and composition is that binary operation. To make it more clear, there is a picture. It's a category of strings depicted on a diagram. It's just 1 object and infinitely many arrows, which is pointing to that 1 object. Okay. Now, maybe even more interesting example: set category of all of the sets. So objects are all the sets, and arrows are functions between those sets. Identity is ID function, which does nothing, so it just maps x inside set to the x. And composition is just a regular composition of functions. That satisfies everything we need to form a category. If you'll take some programming language, for example, Haskell, we could build a Haskell category by using the types which we are using there. So objects are types, and arrows are just pure function between them. Identity is just an identity function in Haskell, the same like in set x equal x, okay? And composition is a function composition. Maybe you have some questions already? Okay, I will continue. Let's try to make notion of the function more general, more category theoretic, I guess. Here we could see just regular set function between sets x and y. And what is functions in categories? Actually, those are called functors. And they are not just mapping objects between sets. They also mapping morphism. So they are mapping the relationships between objects. If you will transfer that to the programming, it means that those are lifting the functions to the higher scope. So it's like an F-map in Haskell. Okay? Functors must preserve composition, so they will not tear any relationship between objects. There is some type of like continuity there. Functors also must preserve identities. So, and that's all. Functors, in brief, are just maps from objects to objects and arrows to arrows, which preserve composition and identities. And therefore, they are preserving structure of category, actually. So they map category to the category. Let's try and look at some examples with code. OK, let's look at the trait in Scala. That's a functor trait, which describes the map function definition. As you can see, it just takes FA object, FA type argument, and the function from A to B, and then return back the functor B typed result. So actually, all that map function do here is takes function from A to B and actually maps it to function from functor A to functor B. Do you see that? Okay? See. That's lifting of the function. You could write function for the simple types and lift it to the more complex one. So you don't need to write two functions. You just need one if you have functor. So, for example, if you will take some container list and make some realization of the map function there, for example, I guess that's trivial, okay? Case, some pattern matching with cons and nil. If there is some value, we will just map the function on that value and further recursively, okay? And if nil, we just return nil. Why is that useful, actually? Why? Let's imagine that we have some project, and the project has function from list user to list name. And it must just acquire some names, just list of names of users, okay? But after some time, maybe some dirty little programmer will add the print line there, and maybe even some more. Maybe it will add some ifs there, and ahead. Wait, but what if you will need one more container type? You will need one more function, get roster, for example, names, and there will be some container which I called roster, and it will do exactly the same, actually, but the code could grow bigger, more complex, and more scary, and you will have two scary functions which doing, oh, what is that doing, actually? It just maps, but there are too many trash there, okay? How to rescue the situation? Actually, that is where the functor could save us. As you can see, we can just define the function getNames with on the functor argument, and just return the functor with a name type from that. So functor is a trait which only has map inside of it, and you could do nothing with that. You could just map. That's all. And in idealistic world, I guess it will be great if inside the body of that function we can do anything with that. Just map. Okay, map that functor, and maybe do some operations that are connected only with functor. No print lines, no scary ifs, no log factory there. It must be abstracted away to the other functions, and not giving programmer even a chance to inject the trash inside of that function. And then we just could use that with functor sealed types like list or roster, and one function will rule all the containers and will give us a possibility to use like a name getter there. Okay. So some conclusions. First of all, category theory and programming are very connected one with another because of the composition. Because programming is a composition and category theory is based on the composition. Category theory is a source of useful patterns for programming. We have seen functors, monoids, but there are also monads, lenses, F-algebras, zippers, and more. Also, category theory helps to understand functional programming better. It gives you like a solid foundation, solid scientific foundation for that, for the programming. There is even really interesting results in mathematics, which called Curry-Howard-Lambeck isomorphism, which tell us that, which tell that you have kind of equivalence between the programming language, or if I may say, the type system that is underlying that programming language, to the category theory and to the logical systems. Okay, so there is a deep connections with programming, mathematics, and actually the foundation of mathematics, like a category theory. Also, category theory is in some sense science about thinking. Why? You can see that it's very wide applicable. It could be used in neuroscience, biology, ecology, network systems, optimal control, and etc., etc. I'm not talking about math even now. So why does it happen? I guess the reason is that because our mind just works like that. It just composes problems to the simpler one, because our brain is not a computer. It cannot see the problem globally and in every detail at that moment. Our mind can see only small bunch of the problems at the one moment. There is even a scientific article that we can't concentrate on the more than 7 plus minus 2 problems at one time. So we need to decompose. We just live that way. So in some sense, category theory is more natural to use than the set theory, which was propagated from the end of the 19th century by Cantor and company. So I guess category theory could make a revolution globally in our understanding of the world and science. Okay, I want to thank you, Bartosz Milewski, for those beautiful pictures and a great blog. Please read that. Jan Esposito for his great presentation about category theory. I took some diagrams from that. Also, I want to thank you, Intetex company, for financial sponsorship, and also want to say that we are hiring currently. Please don't hesitate. There are many flyers lying everywhere here. And also I want to say thank you to those two men, Richard Feynman and Jiddu Krishnamurti. Those people, I guess, they were they considered very important concept to be simple and to talk as simple as you can. So I want to say that we need to talk with the simple words and try to have a really deep connection with each other. Okay, now it's time for questions and answers, please. Thank you.
Hi, so thanks for the talk. I have two simple questions. You said that category theory is